website for Annex 57. So by staying here, you're accepting this. Please mute your microphone and leave your camera off when you're not talking. And for technical support, contact Metco, my colleague who is here in the meeting, and the one who received the link from the email. And if you have any questions and comments during the introduction or during the presentations, please share them with all of us in the chat. Questions will be answered after the presentation during the Q&A session. And if we will try to answer all the questions, if you have remaining questions, they will be answered in written by the presenters. And please avoid to have a parallel discussion in the chat, because then it will be difficult to find the questions. My name is Caroline Hagen-Stignor, and I work for the Heat Pump Center. I will explain that later. The Annex 57, that this project that will be presented now with a long title, it belongs to it's performed within the Technology Collaboration Program on Heat Pumping Technologies within the IEA, and I will explain what this is. This is a technology collaboration program that has been going on already since 1978. It is an international framework of cooperating and networking for different actors working in the field of heat pumping technologies. So it's a forum for exchange of knowledge and experience. And it contributes to technology improvements by performing research, development, demonstration, and deployment projects. At present, the TCP has 20 member countries, I can see here, in America, Europe, and Asia. And within this TCP, we're handling heat pumping technologies and include such for heating and cooling, for air conditioning, and for refrigeration. It covers applications in residential and commercial buildings, in industries, in thermal grids, in cities and communities, and also in other type of applications. This picture here shows how the TCP is organized. So start with, there is an executive committee, which is the board of the TCP with one vote per member country. And this committee comes together and meet 2 times per year. In most of the member countries, there are national teams, which are organizations representing national activities working with heat pumping technologies, and that is a forum for discussion, networking, and creation of new ideas for future collaboration projects. And representatives from those teams meet at national experts meeting. And then we have in the middle here the Heat Pump Center, which is the central program office, the communication center for the TCP, which I work for. And then we have, most importantly, the what we call the annexes, the different collaboration projects in which new knowledge is elaborated through collaborative work, performing research, development, demonstration, and deployment. And we do work a lot with communication and dialogues. It's mainly from the projects, the annexes, and also the Heat Pump Center. So we have, when the projects or annexes are finalized, the reports are openly published on the HPT website. We also publish regularly the HPT magazine, and also the HPT newsletter. It's only digital. We run a website, and we're also active on social media, such as LinkedIn, X, and also WeChat in China. And every third year, the program organizes the IAEA Heat Pump Conference. So last time it took place last spring in Chicago in US, and the next one will take place in 2026 in Vienna in Austria. Besides that, we organize, as I said before, national experts meeting, workshops and webinars like this one, and we provide support to different IAEA publications with input of data and review, and also other outreach activities. As I said, the Heat Pumping Technologies magazine and newsletter, there are 3 issues of the magazine each year, and here you can see the issues for 2024. We have one that will be published later this week with the topic Heat Pumps Unleashing Flexibility and Sector Coupling amidst electric grid transformations and strategic investment. And then we have other topics for later this year, one about how to extend the working envelope of heat pumps, and the third one about heat pumps revolutionizing retrofits. And if you are interested in providing articles for this magazine, please contact Metcal here. And even more important, if you want to subscribe to the magazine, you're still not a subscriber, we will post the link to set up for subscription in the chat. So if you do that today, you will have the next issue published later this week. And as I said, my name is Caroline Haglund Stignor. I am organizing this webinar together with my colleague Metcal, who will moderate the webinar, and Emilia Pisande Berlin, who has also sent out the invitation to many of you, and of course with and all the task leaders from the annex. Thank you. And it's will you share, Metcal?
Yeah.
No, I'll share it again.
Okay. Yes, we're going down to slide 4, Metcal.
Yeah.
5. Okay. Shall I try?
Yeah. Give me 1 second. Okay. Yeah.
Just a moment. Just a minute. I'll try. Can you see my screen now?
No, I thought I shared.
Okay. That's okay. Yes. 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 I'll present the Annex 57 flexibility. The objective of the Annex was to provide an overview of how heat pump technologies can create flexibility in thermal network and also into the electrical grid. The scope was originally that we were going to look into heat pump technologies in combination with district heating, but at the start of the Annex was the individual heat pumps also included into the Annex, and that meant that the scope was widened. We are looking into the markets, that is task 1, and potential, the cases, and we're collecting some cases. We're looking into concepts, assessment, and also business case, and then we're having some dissemination. The project was started in 2021, and it was finalized here in December this year, and here in the spring we have been putting our final hand on the reports, which you can find on the Heat Pump Center's webpage. The participants is Austria, Denmark, where DTI is the operating agent, and then is Germany participating with Fraunhofer, the Netherlands participating with RVO, and also Sweden is participating in the annex. Yes. From Austria is the Austrian Institute of Technologies participating, and also Technical University Wien. And from Denmark is the Danish Technological Institute, the Danish Technological University, Aalborg University Center. Johnson Controls was a part of it in the beginning. And then we're having Plan Energy, and also Danfoss is participating. And from Germany it is Fraunhofer, and from the Netherlands it's RVO, and from Sweden is it Halmstad University. Yes. We're having some tasks here. The first one is task 1, energy market analysis, where we have made some national reports which are uploaded on the web page. And then there is also an article from Aalborg University regarding the market, and also some simulations. I'll tell you a little bit about that. A summary report of these national report, and that is also finalized. Then we are having in task 2, we have collected 28 best practice examples where we're describing existing projects with flexible solutions with heat pumps. And yeah, we are delivering 2 pages and also a detailed description and report. And then we're having a task 3 report, which is regarding concept development of representative and promising solutions. And then we have task 4, which is flexibility assessment and analysis of different options. And then we're having task 5, which is business models development and evaluation of innovative concepts. And there we have also made a task 3, 4, and 5 report. And then we're having all the dissemination. We're having the annex web page. We have had a workshop in Chicago at the conference there, and then we're having webinars today. Yes, we can shift. In task 1, we are making a market analysis of the market trends, mainly regarding flexibility and also the electricity market. And there is also made an article from the Aalborg University, which will be published and uploaded a little bit later on. But we are having the preliminary article at the moment. Yes, shift. And in task 2, we have collected best practice examples. We're having 28 cases. There is a long description on all of them, and also a short description with a summary of the projects. And you can find all the projects on the web page. Shift. Yeah, we can shift back to. And in task 3, we're having describing the concepts for heat pump flexibility, and also solutions with some good examples where heat pumps are creating flexibility and making a solution for flexibility. Yes, and we can shift. Yeah. And in task 5, we have flexibility assessment and analysis of different options, and that is mainly we are describing how you can create flexibility and also deliver ancillary services into the market with the heat pump. And then we're having task. Yes, shift. In task 5, we're having the business models, where we're describing different business models and also the barriers and opportunities. Yeah. The main result of the project is that the market is growing, and there is a larger need for flexibility in the electrical grid. We can also see that the market for heat pumps in district heating systems is growing, and in Europe, we can see that there is a potential that heat pumps can cover from 16 to 38% of the annual production in most of the market. And it's also shown that the heat pumps can act in the ancillary service market, both with the small heat pumps, but also with the district heating heat pumps, and especially if you combine them with the electrical boilers. And we can also see that we have some projects where it's described that we can together with we can provide heat up to 90 degrees with the heat pumps, and that could be delivered into the district heating network. That was the main results of the annex. I would say a lot has happened during the project period. When we were starting in 2021, there was not a lot going on regarding flexibility, but here in the last 2 years, a lot of results and also a lot of projects has been going on, which shows that the flexibility in the market. Yes, we can shift. I'll tell you a little bit about what we have gathered of experience in task 1. Yeah, we can shift. What we can see, and this is taken from the IEA Outlook report, is actually that the electricity demand is increasing, both in China, United States, in Europe, in India, and also in Asia. And we can also see that a lot, for example, if you're looking into Denmark, and also in Europe, is that a lot of wind power is being produced and will be produced in the future, and we'll also get some PV power into the electrical grid. So we're also having an increasing electrical demand because of the electrification of the society. Shift. Yes. We can also see that we have a market development and increase use of heat pumps. This is from Austria, where we can see that they expect to increase the number of heat pumps towards 2050. But they will be combined with other energy sources. We can shift. For example, if we are looking into Denmark, we can see that development of installed heat pumps has increased a lot since 2019, and that is the large-scale heat pumps implemented in district heating systems. And if we are looking into the transition which is going on in the Netherlands, we can also see there will be an increase of both district heating, but also electrical heat pumps and hybrid heat pumps. We can shift with them. Yeah. We can also see that there is an increasing need for flexibility. This is from the IEA Outlook report, and that will increase when we are looking towards 2030, both in United States, the European Union, but also in China and India. And we can also see that when we are looking into the national reports here in this project, that the need is increasing. That is for the Danish market, where you can see that the capacity is increasing towards 2032. We can shift. Yes. The technology mix that will deliver ancillary services in the future, yeah, there can be heat pumps. That is the blue part here in the bottom. This is from the Danish energy grid, and they can deliver both upwards regulation and also downwards regulation. Another technology that will come here in the future and maybe take over a part of of the ancillary service from the large-scale heat pumps is the Power-to-X technology. And this is how it's going to look in the future. Yes, we can shift. In the future, we will have a diversity of actors. When you're having a low production or low production with renewable energies, well, then we need heat pumps, maybe also power plants, batteries. And when you're having a high production, for example, from the PV panels, then you definitely need the heat pumps to take and consume electricity, but also you can also use electrical boilers and the Power-to-X technology. Yeah, we can shift. One of the barriers for implementing heat pumps in the market is actually the price structure of energy, where we from the German national report could see that if we are looking into the price of the oil, and you can see that the taxes is not as high as they are on electricity, where most of the price for electricity is mainly tax and also grid taxes. Yes, that was some of the results from task 1. If we're looking into the development of the market and the future of district heating and heat pumps, yes, we can shift. Then we have made Aalborg University have made a survey of the installed heat pumps in district heating system, and they have also made a market review. They had some older data from an older project, and these data has been updated within this project. They have made a lot of data collection from the large-scale plants, together with the Plan Energy, Danfoss, but also the European Heat Pump Association. They really tried to reach out to get information. And then they have made a modeling of the energy system for the EU 27 countries, and they have used energy plan to model and simulate how the energy would be in the production would be in the future. And then I've made this article where you can read about it. Yes, we can shift. If we're looking at the district heating levels toward 2015, we can see that there is there's really that the amount of district heating that could be implemented is around I would say from 35 to around 50% in most of in the EU 27 countries. In some of the countries is the high implementation of district heating in which is supplying the society and the houses, for example, in Denmark and also in some of the Eastern European countries. But the potential is very high for implementing of district heating. We can shift. When we look at the heat pump coverage in the district heating system, then we can see that depending on whether we are looking into we're looking into base load scenario or a low waste scenario, is the district heating share is varying from I would say 16 to 38% of the production of district heating produced by heat pump, and that actually means that the heat pumps can cover a lot of the district heating production. Yeah, I'll say almost yeah, from 25 to 38% of the district heating production, depending on the concept that we're looking into. They have also been making a simulation. We can see that on the next slide. How the district heating production would be based. That is also for the EU 27 countries. Both they made a 2030 scenario, but also a 2050 scenario. And what we can see is actually that if we look over time, is the heat pump share of the district heating production is actually increasing. That is the light blue area on these graphs. So I'll say the future for heat pumps in district heating system seems quite bright. And that is one of our conclusions in this project. Yeah, we can shift. They have also made a survey on the technologies, both the refrigerants, what is the performance level, also depending on source temperatures. Here you can see two tables. One is for CO2 units, and another one is for ammonia units. So there's a lot of work done here. We can shift. Yes. That was my presentation from Aalborg 2, and now I'll leave the presentation to Vibke from the Danish Technological University.
Yes, thank you. I will share my screen. Okay. Do you see the slides correctly?
Yes, we can see it.
Perfect. Okay. Yes, thanks for being here today. I will talk about flexibility from large-scale heat pumps. This is mainly related to task 4, and I am, of course, only one of the many people that have contributed to this task. And this task also covered small-scale heat pumps, which you will hear about later on. Yes, so before I want to dive a little bit deeper into what we mean by flexibility, into large-scale heat pumps, I want to explain what we mean or what we understood in this project by flexibility, because flexibility in itself can be many different things. It is a rather vague term. So here we divide it between thermal flexibility, which is the ability to adapt the heat uptake or the heat output, and it could also refer to the ability to adapt the delivered temperatures. The other kind of flexibility, which was in the focus here, is electric flexibility, which is the capability of any unit to adapt the consumed electric power at a defined node in the grid. We can divide between short-term, mid-term, and long-term flexibility, where short-term would refer to a time range of seconds to hours. Mid-term would be days to weeks, and long-term, monthly or seasonal flexibility. In this task, we mainly focused on short-term electric flexibility, and we can use 3 main variables to characterize the flexibility of demand-side units, or also of production units. The first one is the power provision capacity. So that is how much can we adapt the power uptake of our heat pump in order to provide flexibility to the grid. Then we have the energy provision capacity. So that is the energy storage potential related to the flexible operation. So that defines for how long can we sustain the deviation of the power uptake in our system. And we have the ramping rate. So how quick can we react to to calls from the electric grid and adapt the power uptake. Yes, when we talk about electric flexibility, we can divide between implicit flexibility and explicit flexibility, where implicit flexibility is the voluntary adaptation of the power consumption by the consumer as a response to a price signal. This could, for example, be variable electricity prices or variable grid tariffs. And then we have explicit flexibility, where the flexibility provider or the demand-side unit operator has an agreement to deliver flexibility. And this agreement can have different forms. It may be bilateral agreements, so directly procured flexibility. It may be ancillary services to the TSO, so the transmission system operator of the electric grid. These are balance services that are traded on specific markets and are activated upon calls. And then we can also have local flexibility markets. There are some examples in Sweden of this. And conditional agreements both can help to avoid congestions locally in the grid. I will now go a little bit more into detail with the ancillary services. So as you probably know, we need to keep a balance in the electric grid between the power generation and the power demand. And our primary tool, of course, are the energy markets. So we trade energy on the day-ahead market, the intraday market, and the balancing market. And then if there are still deviations during operation, the ancillary services come into play. So when the frequency deviates because of an unbalance between generation and demand, the TSO reacts by activating these ancillary services, which are divided into primary reserve, secondary reserve, and tertiary reserve. These services differ in the required ramping times, where the primary services require very short ramping times of below a second up to 150 seconds, depending on the service and the region. Then we have the secondary reserve, which requires ramping times of up to 5 minutes and needs to be sustained longer. And the tertiary reserve, which needs to be activated within 15 minutes and serves to finally restore the frequency if it has not been restored before by the secondary reserve. Then I should mention that we divide between upwards regulation and downwards regulation, which is a little bit tricky for demand-side units because it's defined from the generation perspective. So if I mention upwards regulation, what I mean is that we reduce the power uptake of our heat pump. And when I say downwards regulation, we actually increase the power uptake. So let's get back to the large-scale heat pumps. So what we meant here in the project by large scale, that was centralized heat pumps in thermal grids. And using large-scale heat pumps to provide flexibility services to the electric grid has the advantage that we have a larger regulation power capacity per unit. We typically have large thermal masses coupled to the heat pump in form of a district heating grid, the connected buildings and thermal storages in the grid. And we have professionally managed units that often already act on different electricity markets. So we have the control and communication infrastructure in place. A disadvantage that is sometimes seen is, especially for existing large-scale heat pumps, is that they have not been designed to act flexibly. So they are most often not quick enough to provide at least these faster ancillary services, which of course does not mean that they cannot adapt their load according to spot market prices. However, in order to provide short-term flexibility, we found that the requirements for the heat pump are that it should be connected to storage, so that there's actually a source of flexibility, you could say. The heat pump should be efficient in part load operation. it should tolerate high numbers of starts and stops, and it should have fast reaction times. These, of course, depend on the service that the operator wants to supply. And it should be possible to measure and directly control the power uptake of the heat pump. So, yeah, related to that, we found that, okay, the first requirement that the heat pump needs to fulfill is, of course, that we can control the capacity of our unit. This is typically done in any heat pump or in any large-scale heat pump, but the capacity control is designed such that we control the heat output. This may be directly or indirectly via control of the source outlet temperature, but typically we do not control the power uptake directly. This may, however, be necessary depending on the service if we want to provide a very precise control of the power that the heat pump takes up, and thereby the regulation power that we can deliver. The reaction times depend on the type of capacity control. So the ones that we see most often in large-scale systems are either multiple parallel compressors which are operated on and off, or variable speed drives, or it may also be a combination of both, where you have N-1 compressors operated on off and one with a variable speed drive. In principle, both can regulate relatively quickly. What can make the ramping of the compressors slow is waiting times, and these may, for example, be caused by decoupling of cylinders, which can only happen at specified rotational speeds. It may also happen depending on the control of multiple parallel compressors, if there is a restriction or waiting time in between taking one compressor out and taking the next one out. Yes, then we have turbo compressors, which are typically very fast in changing load. Yes, there are, however, some factors limiting the ramp-up times, and yeah, we took out the ramping times here as kind of the critical dimension out of these flexibility variables for large-scale heat pumps, because that is where we need to work on to make them faster to be able to act on these markets. So factors limiting the ramp-up times are the cycle configuration. So it's the cycle complexity. The more complex the cycle, the more components we typically have, and the more control loops we have that need to be coordinated in a good way to keep the system stable, and this can make the ramping slower. Then we have the thermal mass of the components. So when the thermal mass of the system is large compared to the energy flows that we handle, we have a thermally slow system. And then, as mentioned, the compressor type and number. There may be limitations due to stress and wear in the components, like a maximum allowed temperature gradient in heat exchangers. This is especially relevant, of course, for high temperature heat pumps. As here we need to increase the temperature by a lot more than for district heating, for example. Then there's factors like reduced lubricity at cold startups, so lubricity of the oil, which can increase the wear of the compressor. And then there's factors like that the too quick ramping, also in between different part loads, can result in pressure fluctuations, which put stress on the components and can even lead to unstable cycle controls if we do it in a too extreme way. Yeah. Then we have the controller setup. This is probably where the most can be gained if the controller is designed and parameterized with the aim to allow a fast operation. Yeah, here we can gain a lot of regulation time, you can say. This includes the type of capacity control, the pairing of the controllers, and the parameterization. We have the refrigerant, which plays an important role because on one hand, the refrigerant directly plays into the required complexity of the cycle and how many components we have, which kind of refrigerant holdups we need in the system. And on the other side, it dictates with what kind of superheating we need to operate. And this is especially relevant if we want to be able to ramp very quickly, as when we ramp down, we increase the evaporation pressure. And this may lead to problems with droplets in the suction line if we operate with very low superheating, depending on the type of refrigerant and the gradient of the saturation line of the refrigerant. There may also be, you could say external factors or factors related to the neighboring systems. So limitations of the secondary side, so the minimum or maximum gradient of temperature and load that the secondary side can accommodate. And there may be limitations of the startup current, which limit how fast we can actually start up the compressor without overheating the electric motor. And then the initial conditions play an important role. So a warm startup can reduce the ramp-up times because we don't need to make sure to warm up the cycle before we actually start up. And this can be ensured by keeping the evaporator and condenser in contact with the sink and source streams, and by preheating the compressor block, the oil reservoir, and the suction line. Yes, and here it should also be mentioned that the time to start up the secondary streams can actually be the limiting factor. Other aspects related to flexible operation that are often mentioned are the required standstill times. So when we shut down a heat pump, typically we need to allow the refrigerant to settle in the foreseen vessels in the system. This is necessary so that we ensure a safe and stable startup the next time. So this, together with the risk of overheating and increased wear on the electric motors, forbids a cycling operation where we switch on and off all the time. In that case, if that was necessary to fulfill the specific flexibility service, it would be better to regulate the load but keep the heat pump in operation. Yes, then for the thermal flexibility, of course, the temperature flexibility is interesting, and this is given by the compressor envelope and the material restrictions. This includes also the allowable oil temperatures and the thermophysical properties of refrigerant in the secondary medium. Yes, I now brought some of the examples that we looked at in the annex. The first one is a two-stage ammonia heat pump, relatively small with 800 kilowatts thermal. And it is connected to a large-scale storage tank and two electric heaters. And here the purpose was to test whether this could be operated on the FCRN market in Denmark, which is a primary service with a required ramping rate of 150 seconds. And you can see in the upper diagram the startup times and shutdown times, where the startup times are in the range of secondary reserve, so not primary but secondary, so with around 5 minutes startup time. But then after adaptation of the cycle control, it was actually possible to reach ramping times from maximum to intermediate load within 150 seconds. This was just a demonstration project, so it is not operated in this way in practice. The second example is the one that Sven has already mentioned, a CO2 heat pump in Sønderfælling, also in Denmark. It is a transcritical cycle with an intermediate pressure level to remove flash gas. And it has multiple parallel compressors for the capacity control and a nominal capacity of 3.3 megawatts thermal. And here you can see in green on the diagram the allowed ramping times for the secondary reserve and the results for this heat pump. And we see that it was actually possible to certify that this heat pump can deliver the secondary reserve, which is really nice. And as mentioned before, it is the first one to be certified in this way. These quick ramping times were achieved by adapting the control. So the pre-warming of the secondary, using the secondary streams was reduced, and the controllers were parameterized with the aim of fast regulation. And the third example is a very prominent one, which you probably have heard about in the media. It is the CO2 heat pump in Esbjerg, and here we only had the factory assessment test results available, or yeah, that is what has been published. It is a CO2 cycle 2 with the turbo compressor expander, and you can see the cycle setup in principle is very simple. And together with the turbo compressor, this allows for a quick regulation. And in the factory test, it was shown that it is possible to regulate with up to 9 megawatts per 30 seconds, which would be enough to supply primary reserve. Yes, so that would be very interesting to see the results from the real side, where this is demonstrated. So with this, I want to thank you for your attention, and yeah, please do not hesitate to contact me or the other authors in case you have any questions. Thank you so much.
Thank you, Webke. Any questions? We have a few minutes until the next presenter. And can I also remind, if you have any questions, please write them in the chat so we can read them to the presenters, and we will make sure we answer most of the questions that you may have. I don't see any questions so far. So I guess we'll go to the next presenter. Dietrich, if you're ready, please share.
I hope you can see my slides.
Yes, we can see it.
Perfect. So also very warm welcome from my side, from the German team, and I'm quite happy here to be able to present. Let's see. Now it works. The best practice example of flexibility created with heat pumps. So it's a task 2, and the task leader for this task were from the team Germany, Axel and me, both from the different Fraunhofer institutes. So we had the honor to collect all the different cases, the different examples between the different countries here. So the best practice examples has been notified or published via these 2 pages. Sven also showed them very briefly. For most of the cases, we have additional documents with much more detailed information. So please check the homepage with a practice example. Then you can read the 2-pager for a short overview, and for most of the cases, also the additional documents, and read more about the layout of the different examples. So some statistics. In total, we collected 28 cases, or we documented it with the 2 pages, and also with the longer versions of the documentations. We have a quite even distribution between the different countries, participating countries: 5 from Austria, 5 from Denmark, 7 from Germany, 5 from the Netherlands, and 6 from Sweden. So most of the examples are with larger heat pumps, what Wiebke just explained, but also we have quite a high number of smaller scale or small scale heat pumps. documented here in this documentation from the different cases. And in total, we have also 5 design studies. So it's more just checking out and describing the plannings, not the real implementation. And we also have 1 lab scale system, which is not meant to be productive in the future. So it's just for testing purposes. Just to give you an overview about the thermal power and maybe also the source temperatures of the different systems. So we have just 1 very large system with 600 megawatts, but the main or mainly the systems are much smaller. So maybe you check it out here. So there are maybe 1 or 2 gigawatts are the normal projects, and with source temperatures varying from 10 to about 60 degrees C. So we have a high range in thermal power and also some ranges for the source temperatures. For more details, please check the different cases. Just to get more details from this perspective. Axel, I am hand over to my colleague Axel.
Yeah. Thank you, Dietrich. I will now present you some cases from the perspective of the German team. And I will point out 2 demo cases and start with the project overview of the Smart District Karlsruhe-Durlach, as it is called. You will see here, you find some links considering the project webpage and the recently published presentation at CISPAT last year. To get some more information on the slide, you see a picture of the district of the quarter, where you see the buildings and the main generating units are marked in here as it has been planned, and because it is a project that is still under development, you see that maybe you can go to the next slide, Dietrich. That not everything has been realized as planned. Currently, it is being driven with a heat pump of about 70 kilowatt at a station in 1 building, and a CHP system of about 50 kilowatts. And you see especially another gas boiler that is operated there as well. Next slide, please. To get an impression of the site, you can see in the picture the district heating as it is typically being laid out, a CHP, PVs and heat pumps as they are installed in this demo site. As I mentioned just recently through a publication, the first operation period has been published. That has been conducted in a scientific monitoring that has been done through the last year. Next slide, please, Dietrich. On this slide, you can see the energy flow, and what you can realize on the left side is that there's quite a large proportion of natural gas involved in this supply of the district, and it becomes clear that there are quite high losses of thermal energy that are due to misoperation of the hydraulic system that still occurs. And it becomes also visible that the heat pump system that you find at the bottom of this picture has quite a, let's go back maybe, anyhow, has a small share in the domestic hot water preparation. So there are still some adjustments in the control scheme to be done. And now you can go to next slide, please, Dietrich. And you see that this energy management system is still under an optimization phase. Main focus in here is like to increase the self-consumption of the system. And you see on this slide that the CHP system does cover quite a large proportion of it, and especially during summertime, it is to be noticed that the share of the heat pump is quite low, as the cover of the domestic hot water preparation is low in the total coverage of PV and the heat pump system. But the self-consumption, the self-sufficiency rate is in total quite high. That is the main objective of the EMS system. Next slide, please, Dietrich. So as you can see here on the final slide, you can get some numbers from the monitoring of the system. And as I mentioned, in the next phase of the research, the energy management system is about to be optimized and rolled out in another period. And I would like to thank the colleagues from University of Freiburg and INATEC that did this research, and the Federal Ministry of Economics that supported this work. Next slide, please, Dietrich. The other project I would like to introduce is the so-called Real Laboratory large-scale heat pumps that has been conducted for now about almost 2 years. And you can see in the top of this page 2 of the largest heat pumps installed in district heating systems in Germany that are operated on temperatures of 90 to even 99 degrees centigrade, and that produce heat at about 20 megawatt thermal. In the lower part of this slide, you see 3 other machines. Their heat is being produced in an ammonia-based cycle at a range of 80 to 88 degrees centigrade, and at a range of 1.3 to 1.5, more or less, megawatt thermal. Next slide, please. Now I would like to point out a little bit more in detail the demonstration sites where these heat pumps are being installed. On this page, you can see the demo site of NBW in Stuttgart, where more or less 20 megawatt thermal output large-scale heat pump is being installed of Mitsubishi by the producer of Johnson Controls. And what makes this situation over there very interesting is that the plant site is a historical, very old place, so it is really challenging to install such kind of machines under running thermal power plant. And you can see the key indicators of this power plant at the first at the top of this page, what is still under operation when you install such a heat pump. So it's a very challenging process, and the monitoring phase has, from the point of research, just started over there. Next slide, please, Dietrich. Another spot I would like to introduce with this slide is the Großkraftwerk Mannheim power plant that is taking part in our research through the MVV. You can see it is quite a large site with a high electricity and thermal output. And a large-scale heat pump of about 20 megawatts thermal of Siemens has been installed over there. And the special point of view is that a large thermal energy storage is coupled to the heat pump and to the system, so that gives the entire system quite a good point of flexibility. Basically, the infrastructure is very well at this site, so it was more or less comfortable to install such a system in this coal-fired site. Please, Dietrich, next slide. And finally, I would like to introduce the site of Stadtwerke Rosenheim. That is currently a waste-fired boiler site with some CHP units in addition. In this place, 3 large-scale heat pumps with a thermal output of 1.5 megawatt thermal have been installed that are ammonia-based. And for this site, first measurement results have arrived as the part of the research team that show that a 15 minutes ramp up is possible for such systems. So analyses are still ongoing and will be published within the ongoing research of our project. And you will find the information through the website that Dietrich Schmidt has just published. And yeah, just please go to the next slide. So I would like to finish this. And as you have seen, all these demonstration sites in real life need to be challenging quite some aspects due to the fact that installing such systems is not so easy. So there's little standardization and so on. So to get really to the point to approve the systems under its measures of flexibility still takes some time, as let's say optimal standard operation has still not been conducted for all of the systems. So the optimized dispatch strategies are still under development and are to be analyzed in the next time. So thank you very much. And Dietrich, you could close this presentation with your last slide.
Yeah, thank you from my side. So I think we still have some time for some questions, right?
I guess so, yeah.
Yes, thank you. We have some more time. So if there are any questions, I've noticed there's 1 or 2 questions in the chat. One was to the previous presenter, so I guess Webke, you can directly respond on the chat to the person who asked, where he says, why are you using 2-stage of expansion? But I'm not sure if this is directly to the current presenters. There's another question which says, what is the state of art in the end of life management of heat pumps? Perhaps would you be able to say something, or is this? Otherwise, you can the person who wrote the message or the question, if you want to clarify what you meant, or
Hi, hello. My name is Reena. Am I audible?
yeah, we can hear you.
Yeah, so similar to the sort of solar photovoltaics, because right now we are thinking more into the end of life management. So since heat pumping technologies is getting more pronounced in the energy sector, so I think I was curious to know how this end of life management, or like the circular economy of heat pumping technologies, will happen in the coming years.
Thank you. If any of you wants to respond, otherwise we will make sure we write or respond to you directly later after the presentation.
Yeah, anyway, it's fine with me. Like.
Yeah, thank you. Any other questions for the current presenters? Okay, I mean, if you do have questions, you can always write them in the chat and we'll make sure they're answered as we go along. So thank you so much for your for the presentation. So we will continue to the next presenters. Marcus and Marian. Yeah.
See if I can share my screen. Do you see it and in the correct format?
See it. Yes, thank
Perfect.
you.
If I can change slides. Yep. Okay. So I, together with Marion, will talk a little bit about flexibility from small-scale heat pumps. So I will start with sort of an introduction and continue with technical aspects, and then Marion will take over and talk about policy and communication, I think. But as an introduction, we will focus here on heat pumps in single-family buildings with hydronic heating systems, in other words, ground source, air-to-water, and exhaust air heat pumps. So air-to-air is not included, and the main reason is that it's other difficulties when it comes to control the backup heating. At least in Sweden, you have electric radiators as a backup normally, and they are operated independently on the heat pump. So you have a risk that if you, for instance, switch off your heat pump, it will end up that you only start the radiators instead. One also have to keep in mind that a heat pump for a single family building can only deliver a quite small amount of flexibility to the power grid. So you need a number of heat pumps aggregated and controlled together to get a decent amount of flexibility. And then you have these aggregators that can use their pool of heat pumps to deliver different kind of services to the power system. And both increase and decrease of the power consumption can be of interest. You also should keep in mind that flexibility is all about moving electrical loads in time, at least when it comes to heat pumps for single family buildings. And then normally you don't have any backup system depending on some other heat source, as you many times have for a heat pump in a district heating grid. So when the heat pump is stopped, sooner or later you have to run your heat pump harder to compensate for the missed heat production. And it's very important that you handle both the decrease and increase in a good way in order to keep the performance high. I think in the next slide we have an example. This is from a Swedish research project called Homes for Flexibility, where in this case 4 heat pumps was controlled together. It was 2 air-to-water and 2 ground source heat pump, I think. And during the first part there, they run as natural, and you see the aggregated power consumption for the heat pumps. And then at 6 o'clock they stopped the heat production for 2 hours, and then they had 4 hours to compensate for the loss in heat production. So in the first step, when you switch off your heat pumps, it's one important step is to have a fast reaction, that the heat pumps react fast, but also that it don't start when it shouldn't. But in the second phase, it's important to also control the power consumption in order to avoid the auxiliary heater to start, but also to control new power peaks, so you don't get just new problems later on. As Ripke told about, there are a number of different flexibility services. I will in the coming slides focus mainly on the TCO's ancillary services, partly on the local flexibility markets, and the reason we focus quite a lot on the TCO's services is that there are clear rules already today how fast the heat pump or whatever flexibility resource you have has to react and what it has to fulfill. Implicit flexibility is there are already these products on the market that can adjust their power consumption based on variations in electricity price or grid tariff and similar. We had an now ended research project in Sweden where we made an interview study with 4 of the Swedish heat pump manufacturers. and it was very much focusing on the technical possibilities and constraints when it came to flexibility. And we saw that in general they had a quite common ground in the technical limitations of the heat pumps. Of course, some differences, but in general, quite a common ground. So, starting with a compressor, if you have an on-off compressor, it can be turned off more or less within a few seconds, but the startup time can take up to a minute. And reasons that was mentioned was that they need to start a brine pump first before the compressor can start, or you can have situations where you need to preheat the compressor oil, which also delays the startup. When it comes to variable speed compressors, they are quite slow to both start and stop. It can take several minutes to start the heat pump and adjust the power consumption to the correct level. It's faster to just adjust the frequency of the heat pump compressor. These are things that are probably possible to speed up to a certain extent, but there will always be some technical aspects that limits what's possible. And here one have to keep in mind that until now, that's never been asked for to have a fast control of your heat pumps. It has been better to have a more stable process. So this is kind of new for the manufacturers. We also have the auxiliary heater, which is quite fast to control, both when it came to decrease and increase in power consumption. But in normal operation, you kind of want to use the auxiliary heater as little as possible to keep the performance up. So it's needed some dedicated reprogramming if you should control of the control system, if you should control it rapidly. But otherwise, it's almost always possible to increase the power consumption of the auxiliary heater, and at least during cold spells, it can also be used to reduce the power consumption. But to do this, you need some clear economical initiatives to compensate for the much lower COP values. So if you sort of summarize, when we ask them what kind of services do you think it should be possible to meet with the heat pumps, the manufacturer says that FCRDN or FCRD seems possible to fulfill. That not meaning that they can do it today, but with some adjustments. And the fastest one there, FCRD, needs an activation time of, you shouldn't reach 50% within 5 seconds, so it's quite fast. Another potential problem when it came to small-scale heat pumps is that you somehow need to measure the demand response delivered. And these heat pumps today don't have any power meter installed. So you need to estimate the power consumption in other ways with as high accuracy as possible. And there are restrictions here, at least at aggregated levels, what you have to receive. So we talked about this with the introduced heat pump manufacturers and want to ask them to estimate roughly the uncertainties, what they can manage today. And the answer is that with variable speed compressors, they are quite good, 2 to 10% measured in an inverter. On-off compressors are lowering accuracy. You have to calculate it indirectly, so the estimated to 10 to 20%. The auxiliary heater is relatively good if the voltage is known, so 0.5 to 5%. And installing electrical meters afterwards is expensive, and you need skilled personnel for doing that and so on. So it increases the cost if it turns out that it's needed to measure somehow. It would increase the cost to start delivering flexibility. Another potential problem is cybersecurity. Heat pumps needs to be controlled over the internet to contribute with flexibility in an efficient way. And as for all internet connected devices, it makes them vulnerable for cyber attacks. And as heat pumps has quite long lifespan, new cyber threats will come up, and it will demand updates for quite many years to keep them up and running. And to compare it with something, I think Apple gives their iPads in general like 7.5 years of security updates today. So, and we want the heat pump to live for at least 15-20 years, maybe longer. And a hacked heat pump can cause severe problems, both for the heat pump owner itself, of course, but also for the power system. If you have a large pool of manipulated heat pumps and control them together in a bad way, they can have a significant disturbance on the national power grid. So some short conclusions of the first part. So flexibility is all about moving electrical loads in time, at least for heat pumps in single family buildings. And these heat pumps can only deliver a smaller amount of flexibility, so you need to aggregate them and control them as a group. The heat pump manufacturers interviewed has quite common ground in how fast the heat pump can be controlled. So for on-off compressors, they can stop within seconds, starts about 1 minute. Variable speed drive compressors take minutes to both start and stop. But the auxiliary heater is quick to start and stop. And today's heat pumps lack electricity meters, and thereby we risk a low accuracy to measure the demand response delivered from the unit. And finally, don't forget the cybersecurity risks. Marion, do you want me to continue to?
Yes,
share the
please.
screen, or yeah.
Hello, everyone. My name is Marion Brokker. I'm from the Netherlands Enterprise Agency. And I will say something about the Dutch situation and why connected heat pumps are so important in the Netherlands. If I say something short about the situation in the Netherlands, 90% of our homes are still on gas, natural gas. And policy made us end our national gas production. Of course, there are climate targets, and in the first place, we want off the gas grid. But then we got a new problem, and I will show you in the next sheet. Next one. Because our electricity grid is most developed for gas, we have now a problem in the Netherlands about grid congestion on the grid. And the rollout of heat pumps can be not as fast as we wanted with the off-grid, off-gas policy. And that's why we need now a new national action program for grid congestion. Of course, we need a faster realization of grid expansions, but that goes not that fast. So we need a better use of our grid. It's very important in that case to increase flexible capacity smart solutions as well in the small scale heat pumps as the large scale heat pumps. And while our district heating cooling grids are still 6% of total, we have a big focus also on small scale heat pumps in the residential sector. So we have a new set of incentives in that way. We think of enforcing the ban on electric boilers, drawing up a protocol for grid-efficient installation of heat pumps in large-scale renovations and new constructions. And we want to learn installers across the country to implement this manual. And of course, very important development of smart control hybrid heat pumps in a fast speed time. Next one. As Sven shown, this was our first policy challenge. The gray zone is the gas boiler, and the transition to the renewables should be 1/3 electrical heating, 1/3 especially heat pumps, 1/3 district heating cooling, and 1/3 hybrid heat pumps with renewable gas. As we see in the picture at the right, we see that the growth of heat pumps, it was fast in the last years, but especially the air-sourced heat pumps and the ground source heat pumps were not as fast growing as. And what we think now in the new situation, that the air source heat pumps, especially the all electric ones, are if they are not connected or not using flexibility, it could be that it's not helping us with the grid concession problem. So that's why we focus now on another policy together. From now on, we have to prioritize which can be on the grid first. Before that, it was more the policy first come, first serve, but that's not possible anymore at this moment in this situation. So we have now this co-decision on prioritization space for transport. And first, of course, we want every market player to fix their own problem with solutions. You can think of flexibility themselves or energy storage. Of course, the more safety facilities, they also get prioritized access to the grid, and after that, also the ones like drinking water, education, housing, and also, and that's of course very interesting, collective heating facilities. We now in the Netherlands have this huge support on district heating systems. Next one. And also hybrid heat pumps. So as an enabler for energy transition in favor of all electric heat pumps, air source heat pumps. So we have an action program running. The main goal is 1 million hybrid heat pumps in 2030. We have a lot of program in that way. We do a lot of monitoring. We work together with installers on installation of heat pumps. And at least we also have this impact on the electricity grid monitoring and smart application running. In the next sheet. because in a monitoring campaign, we showed that the impact on the grid, the difference between all electric heat pump and hybrid heat pumps on the 5 coldest days, the load on the electrical grid differs. And that's what we can't use now at this moment. So, and if you look at the share of the heat pump at the different outsourced temperatures, you can see that on the coldest days, the share of heat pumps compared to the gas boiler is low. So this kind of monitoring campaigns helps us in our programs to improve in first place the control between the hybrid heat pump and the gas boiler. So and on the other end, also to promote hybrid heat pumps in certain areas in favor of electric heat pumps. This was the first part of the of this monitoring campaign. We're now running the second part, and it goes like this: everyone who gets subsidy on a heat pump in the Netherlands get a letter from us. Ask them if they want to be part of this monitoring campaign. And now we got already 5,500 people working together with us on monitoring their heat pump to see how the impact of heat pump will be on the grid. And the monitoring campaign is financed by as well the government as the grid operators. Next one. So what we need to do now, the potential flex of heat pumps has to be unlocked in the Netherlands. The Dutch TSO, TenneT, stated in a report that was based on figures of 2020 that the heat pumps in the Netherlands might be an extra electricity consumption in the non-solar and winter periods. And if we do it in the right way, we can grow to at least 3 gigawatts in 2030. But then the heat pumps need to be flexible controlled. So in a latest study amongst the OMEs, a survey where we discuss with them what's the situation now about connected heat pumps and where do you think you want to go in a couple of years. It resulted that the use of the heat pumps for flexibility might be done in 2 steps. First step, use the availability variance of the smart grid readiness, but in the same time prepare as the second step the use of communication protocols at this moment in the market, S2 or eBus, but in a way, in a 2-way traffic to use the heat pumps more flexible. And so in the Netherlands now we are in sort of capacity building where on one way the manufacturers work together with the grid operators to see what they can do in a speed way to have this second step done. But next one. We can't do that in the Netherlands alone, of course, because the heat pump market in Europe is a broader market, European market. So the European Commission is also working on the interoperability of heat pumps. And recently they launched the Code of Conduct in Hanover, and the Code of Conduct covers the electrical appliances that have an energy label, white goods, but also heating and heat pumps and air conditioners. And And it follows use cases like the flexible start, the monitoring and limiting of the power consumption, and the incentive to table-based power consumption management, and the manual operation of energy smart appliances. And the first 10 companies they signed in April 2024. And of course, it's good because it's an international European initiative. And I hope more manufacturers will sign this. That would be good also for us. Next one. So I talked to our grid operators and asked them, what do you wish for this grid efficient heat pumps? What do you think what the market should do, or the manufacturers and government together? Well, they said, first of all, give the clarity about the system perspective for grid efficient deployment. And the method of the control, it's important for them to know if it's locally to the heat pump itself or by an API to a management platform of the heat pump or a home energy management system. Also important, do it not for yourself as a manufacturer, but try to work together in a European standard, because the reason I mentioned before. Robust is very important, provide local connectivity as well, because if you only use cloud only, and there is outdated technology or bankruptcy, then it might not be desirable anymore to manage. The platform provides a flexible platform solution in the heat pump. It must be able to support new standards and requirements with software updates. That's also what Marcus mentioned before. And of course, the interchangeability with other devices in the house. You can think of the electric car, but also the energy storage. It might need to communicate with these other systems as well. Cybersecurity we mentioned before, but there is upcoming legislation such as the RAD 3.3, and which will include the cybersecurity requirements. So please follow this. And this learning platform, support and learn from open source and early adapters. However, do not wait for complete clarity about the system perspective to start with work out the standards for control. That's what I wanted to say here about the Dutch situation and about these small-scale heat pumps. I hope they will be connected very soon and that we can work together on European level or international level. Thank you.
Thank you, Marcus and Marian. Thank you so much for the exciting presentations. We will take one or two questions since we're slightly running out of the time. We have a couple of questions in the chat, and I'll read them. Perhaps Marcus or Marian, if you want, you can try to answer them. So the first one says, could you explore the required change to existing control systems, particularly if heat buffers are to be included? And it continues to say, how and to what extent can existing heat pumps be controlled externally? What kind of control would manufacturers allow? So perhaps that relates to the survey that you've looked at, Marcus. And
yeah, I think what we will allow, I think that's still under discussion, we will see what happens. But I think something will come. There is just to see who is first with doing something, and maybe it probably will be done in cooperation. There are similar solutions where, for instance, instead of taking over the control of the heat pump, to say send a fake outdoor temperature to the heat pump and make it react in that way, and so on. So there are other ways to go around it. But I think we will see a cooperation between the manufacturers and aggregators.
Okay. Yeah. Thanks, Max. And last one, just quickly. Have you explored the aggregated flexibility of individual heat pumps in a district heating and cooling networks? Is there any example of how much energy flexibility can be achieved in a year? Either you or Marian, would you be able to?
I don't know if I understand the question, because is it then like very low temperature?
Yeah.
Yes. Hi, hello, Rainer. It's your question. Oh, no.
No, it's another person.
Oh, okay.
Yeah.
Yeah.
Otherwise, we have few minutes until the meeting finishes. You can think about it and respond to the message directly.
Read. Yes.
Yeah.
No, das kann nicht sein.
Okay, I think
Müsste da nicht halt neu
Rainer is
ich arbeite auch gerade
in the meeting.
Parallel.
Yeah, I'm muting him. Okay, I don't see any other questions. So we will continue to the next presenter. The last but not least, we have Philip. If you're ready, please share your presentation.
Yes, good afternoon from my side. Can everybody hear me?
Yes, we can hear you and we can see the slide. Thank you.
Very good. Thanks a lot. So I have the pleasure to talk you through the contents and results of task 5 of our project, which is called Evaluation of Business Models and Analysis of Barriers. The target of this task was to discuss technical and non-technical barriers and obstacles that prevent flexibilities to be taken into the market and drawn from small-scale devices like heat pumps. And another target was to derive innovative business models and analyze the existing business models in this field already. An overview was created during the project on general potential applications for flexible heat pump use. We have on the left-hand side the different price signals and fields of applications, starting with the usual suspects, the spot markets, where we have the day-ahead and the intraday markets. A pre-requirement to use these price signals is variable tariffs or day-ahead price projections. Actually, you need kind of a forecast or a projection for the day-ahead price in order to act flexibly on it. And that requires strong coordination between trading department and the supplier, which gives you the tariff actually. Nonetheless, it's quite a low implementation effort of this case, but also rather low profitability actually. So analysis of our project showed that it's not very profitable to run the heat pump against the day-ahead market, for example. Profitability is medium already in the balancing market, so using the primary, secondary, or tertiary balancing markets can be much more profitable for heat pumps, but there comes the additional complication of pooling and pre-qualification. You really need to precisely have a load control which is quite complicated with to coordinate across the balancing service provider, the supplier, and the manufacturer of the heat pump on the three sides. And in addition, you need to do a very precise settlement in the aftermath, and also need to overcome a DSO veto, which is, at least in Austria, the case that the distribution system operator has a veto for devices to provide balancing energy. Imbalance settlement is rather a theoretical concept, but in theory, heat pumps could provide flexibility to reduce imbalance costs. That requires imbalance responsibility in the first place, and also very short-term load control. Is not so interesting because it's high implementation effort and low profitability on the other hand. Local flexibility markets is also something that is not yet in place. So there are not many countries or regions that really run local flexibility markets by the DSO side. It would require also rather high implementation, and profitability is not yet clear what it's like. Probably rather trivial kind of applications of business models is maximize the own consumption. Very low implementation effort there, but it's also not very profitable. But it's quite straightforward to maximize the own consumption within an energy community, for example, using the own generation of PV, solar PV. A business model that is already used, at least in Austria, is using variable spot market prices, so that they head price essentially, which is run by EDM and Avatar, for example. EDM is a heat pump manufacturer, and it offers a control system that runs the heat pump in hours where the electricity price is rather low. It does that together with a supplier called Avatar, and as the illustration suggests, the heat pump is used in times when the spot market price is rather low. Obviously, it needs as a prerequisite Avatar as a supplier, for example, that offers variable electricity prices directly from the power market exchanges. Obviously, you can use two things as a kind of storage to operate your heat pump flexibly. On the one hand, you have the thermal mass of a building, and on the other hand, you could have hot water storage in addition, which makes your buffer much higher and allows for more flexibility to be offered in the market. In terms of innovative business models, we've looked at two cases. On one hand, support of the distribution grid, and on the other hand, provision of balancing services. So heat pumps, in order to provide services to the balancing markets, they need to be aggregated because they're very small applications. And to provide balancing service for the transmission grid, there is typically something as a minimum bit size of, for example, 1 megawatt. So you need to aggregate a lot of heat pumps in order to achieve this minimum bit size. For all those innovative business models, we conducted a business canvas and thought it through what it would be needed in order to implement that. On the right-hand side, it's an illustration from an Austrian research project showing the participation of the heat pumps on the day-ahead market, the secondary reserve, and the tertiary balancing market. And the result was that the secondary reserve was actually most profitable, with a cost reduction of around 10 to 12% compared to a reference case. Obviously, what is the problem that is solved by this approach. In the future, we will expect much more need for balancing due to more volatile renewable energy source production, and this requires also very fast reaction times and high reliability, and heat pumps, which will be rolled out in the future, could provide this flexibility. It provides a number of unique value propositions. On one hand, we can support the electricity grid. On the other hand, we can lower the bill for heating, and in an ideal case, we even get paid for consuming electricity if we participate in the balancing market. There are certain times where the prices become negative, therefore you could get paid for consuming electricity. Customer segments in this case could be all households, basically, once you achieve to aggregate them properly. But obviously, it could be more efficient to approach heating grid operators and larger plant operators. Yeah. A second innovative business model could be local flexibility markets and support the distribution grid. Obviously, the problem that we're going to solve here is that there will be congestions in the distribution grid in the future, and too much electric load will be in the grids locally in the future. Therefore, the solution is to offer interruptible tariffs from the side of the distribution system operator to incentivize curtailment at some points or reduce the load at some points. It's quite easy to implement, actually, in theory, and it can be achieved without a lot of additional costs. But the problems are that there is no direct competition between DSOs, obviously, because they are regulated monopolies. And in the future, there is some gaming potential because the households or the consumers in the grid are the ones who cause a congestion in the first place. So getting paid for it to solve it could cause some problems regarding incentives, actually. So it's the big question whether problems in the distribution grid can be resolved on a market-based manner. Yeah. To wrap up our main findings, the main barriers we identified for the flexibility use of small-scale heat pumps were economic ones, so low savings potentials, for example, on the head market. That is mainly because actually the grid tariff consists also a large share of the electricity bill. So even if you catch low electricity prices, it only accounts for a very small share of your actually electricity costs. On the regulatory side, we identified the problem with aggregation and coordination between supplier, trading, and manufacturer as a rather large obstacle, combined with a minimum bid size, so that on the balancing market, minimum bids of a couple of megawatts need to be offered. Medium barriers are probably the acceptance of end users, because it's to get it rolled out across all heat pump users, a lot of knowledge needs to be distributed in the crowd. For now, it's only for the really technically fine users to use such systems. And yeah, the incentives and informations from sides of the manufacturers could also be more transparent in this case. Technically, there are not so many barriers identified in general. Probably ramp-up times and standstill times combined with temperature in certain situations are probably some kind of medium barriers. Well, to conclude, we found that flexibility provision with heat pumps is a very relevant topic in Europe at the moment. That was already mentioned a couple of times. Some flexibility services have a rather high market readiness level already and can be translated into successful business models in the near future. But it's more innovative, or in the future we expect some business models to come up with regards to balancing services, because that showed the more profitable case actually. And this was already used in some research projects in Sweden, Denmark, Austria, and Germany. And yeah, in Sweden, for example, combinations of FCR and AFR, so primary and secondary, showed the highest cost reductions. In Denmark, it was AFR,
Philip,
and similarly in
Philip,
Austria, it was also AFR.
Sorry to interrupt. We only see a dark, empty slide on your. Yeah, now we see it. Now we see the summary. That's good. Continue now. Sorry.
Very good. Yeah, that was already it actually. So in Denmark and Austria, secondary balancing was the most profitable case, followed by FCR typically. In Sweden, it was FCR that was most profitable. But yeah, in general, we expect some kind of business models involving balancing to be introduced in the future. Well, that would be it from my side. So thanks for having me, and looking forward to any questions you may have.
Thank you so much, Philip, for the exciting presentation. Any questions from audience?
Yeah, I have a question.
Sure.
I'd like to know what's the advantage of using small-scale heat pumps comparing to district heating at medium temperature.
Philip, did you get the question?
Yeah, is that a question directly to me or in general?
Yeah, yes, for you.
Centers? Yeah, well, in the future we expect a rollout of small-scale heat pumps, so we expect a lot of potential to be there in the future. Therefore, that is the ultimate advantage, that if you aggregate across many heat pumps and pool them, you would get a much larger pool to be offered on flexibility markets.
Okay.
Thank you. Any other last question? Perhaps I'll ask you one last question then, if I don't see any questions. So you went through some of the emerging trends or innovative approaches in business models, Philip, in your slides. I wondered if there are any particular business models that you see as particularly promising for the heat pump industry.
Yeah, good question. It is probably a combination of using the day-ahead market and the balancing market, maybe also the intraday market, that is probably most promising in terms of economics. So we would expect some heat pumps to contribute to these markets in the future, but there is still a strong coordination problem to be solved between the supplier, the balancing service provider, and the manufacturer. So those three need to coordinate in the future. That is probably the highest barrier in order to be implemented.
All right, thanks. So thank you so much again, Philip. Sven, before we close before we finish the webinar, if you want to do any closing or last minute updates, I'll give you the floor.
Thanks a lot, Mikkel. And Also, thank you to all the other presenters. I'll say all task reports are uploaded at the heat pump center's webpage, at the Annex webpage, the webpage for Annex 57, and they are in that folder named publications. And the final report will also be uploaded. There's actually a preliminary report there of the final report, but I'll say all the deliveries are more or less uploaded at that webpage. I only need to upload the article from Aalborg, but I need a go from Aalborg before I can upload that. So that, I think that was all. Thank you for participating in this webinar. And if you have any further questions, then you can send them to the project group here. Yes.
Okay. Thank you so much, Sven, and thank you, everyone. That concludes our today's webinar.
Thanks a lot.
Thank you.
Thank you.
Thank you for participating here.